Close your eyes for just a moment and picture the birth of everything, an explosion of energy so unimaginably vast, it set the entire universe into motion. No sound, no light, just pure, unfathomable potential erupting into existence in less than a blink of an eye. This was the Big Bang, the very first heartbeat of our cosmos. But what came next? How did this fiery birth give rise to galaxies, stars, and eventually us? For decades, scientists have pieced together clues hidden in the fabric of space itself, whispers from 13.8 billion years ago that tell a story stranger than fiction. And what they've discovered will bend your understanding of reality itself. From the ripples of cosmic inflation stretching the universe like taffy to the afterglow of creation still lingering in the void, every discovery peels back another layer of this grand cosmic mystery. Imagine a force so powerful it could fling entire galaxies apart in an instant, or quantum fluctuations so tiny they became the blueprints for galaxy clusters. These aren't just abstract ideas, they're the very foundations of our existence, written into the atoms in your body and the stars above your head. And the wildest part, we've only just begun to scratch the surface of what happened in those first fleeting moments after the universe ignited. That's exactly what we're diving into today, 25 of the most mind-blowing, spine-tingling discoveries about the Big Bang and cosmic inflation. Some will make you question everything you thought you knew about time and space. Others will leave you staring at the night sky with a whole new sense of wonder. And a few might even keep you up at night, grappling with the sheer scale of it all. Because this isn't just a story about the distant past, it's about how we came to be and the forces that shaped every single thing around us. So if you're ready to unravel the greatest origin story of all time, let's begin where it all began, with a single universe-shattering moment. The first clue in our cosmic detective story came not from some futuristic telescope, but from a pair of radio engineers tinkering with a strange hissing noise they couldn't explain. Back in 1965, Arno Penzias and Robert Wilson were troubleshooting a massive horn-shaped antenna in New Jersey, convinced the static plaguing their equipment was just pigeon droppings or faulty wiring. But after months of scrubbing and rewiring, that faint, persistent buzz remained, and it came from every direction in the sky. What they'd stumbled upon was far more profound than a technical glitch. They were hearing the dying whisper of the Big Bang itself. This cosmic static, now known as the cosmic microwave background, is the oldest light in existence, a snapshot of the universe when it was just 380,000 years old, glowing faintly after expanding and cooling for nearly 14 billion years. Think of it like opening a time capsule buried at the dawn of creation. The CMB is the afterglow of the universe's fiery birth, stretched by cosmic expansion from blinding white-hot radiation into the faint microwave hum we detect today. It's everywhere, literally. If you've ever seen static on an old television set, about 1% of that snow comes from this primordial light, bathing the entire cosmos in its ghostly glow. But what makes it truly revolutionary is what it tells us about the early universe. Tiny fluctuations in this microwave, see warmer spots here, cooler patches there, are like cosmic fingerprints, revealing where matter first began clumping together to form galaxies and galaxy clusters. Modern telescopes like the Planck satellite have mapped these temperature variations with stunning precision, showing us a universe that was remarkably smooth but not perfectly so. Those slight irregularities, born from quantum ripples smaller than an atom, became the seeds for everything we see today. Without them, gravity wouldn't have had anything to grab onto, leaving the cosmos a featureless void. So when you look up at the night sky, remember, the stars above you, the planets, even your own existence, all of it traces back to those subtle whispers encoded in the CMB, a message from the universe's first moments waiting to be decoded. Edwin Hubble didn't just change our understanding of the universe, he shattered it. In the late 1920s, while peering through the 100-inch Hooker telescope in California, he noticed something bizarre about the faint smudges of light astronomers called spiral nebulae. These weren't just clouds of gas within our Milky Way, as many had assumed. They were entire galaxies, island universes millions of light years away. But the real bombshell came when Hubble analyzed their light. The farther away a galaxy was, the more its light stretched toward the red end of the spectrum, like a cosmic Doppler effect. This redshift meant the galaxies were racing away from us and from each other as if space itself was stretching. Hubble's law, as it's now known, revealed a universe in motion, expanding in every direction like dots on an inflating balloon. The implications were staggering. If galaxies are flying apart today, rewinding the tape means they were once crammed together in an unimaginably dense, hot state, the very essence of the Big Bang theory. It was as if Hubble had stumbled upon the universe's stretch marks, proof of its explosive birth. But here's where it gets even wilder. This expansion isn't just a relic of the past, it's happening right now at an accelerating rate. The space between galaxies grows larger by the second, not because they're moving through space, but because space itself is swelling beneath them. Picture a loaf of raisin bread baking in the oven. As the dough rises, every raisin moves away from every other raisin, not because they're traveling through the dough, but because the dough is expanding between them. That's precisely how cosmic expansion works, except there's no edge, no center, and no oven. Just an endless, stretching fabric of space-time carrying galaxies along for the ride. Hubble's discovery didn't just confirm the Big Bang, it gave us a way to measure the universe's age. By calculating how fast galaxies are speeding apart, scientists traced backwards to that initial moment of singularity, a point of infinite density where time, space, and the laws of physics as we know them simply didn't exist. Yet Hubble's law also left us with haunting questions. What triggered that first unfathomable expansion, and what mysterious force is now speeding it up? The answers lie hidden in the darkest corners of cosmology, where the ghosts of inflation and dark energy lurk. But one thing's certain: when Hubble peered into the void and saw the universe running away from itself, he handed us the first piece of a puzzle that's still being solved, one that rewrote our place in the cosmos forever. Just moments after the Big Bang's explosive birth, the universe was still too hot and dense for atoms to exist. It was a seething ocean of subatomic particles, protons, neutrons, and electrons racing through a plasma so thick light couldn't even travel through it. But as the cosmos expanded and cooled, something extraordinary happened. Within the first 3 minutes, conditions became just right for the first atomic nuclei to assemble, like microscopic Lego blocks snapping together in the primordial chaos. This brief window, known as Big Bang nucleosynthesis, forged the very first ingredients of matter: hydrogen and helium, with trace amounts of lithium. The precision of this process is staggering. Calculations show that about 75% of the universe's ordinary matter became hydrogen nuclei, single protons, while roughly 25% fused into helium nuclei, each containing 2 protons and 2 neutrons. These numbers aren't just theoretical guesses. When astronomers measure the composition of ancient gas clouds or analyze the light from distant stars, they find nearly identical ratios. It's as if the universe left us a receipt from its earliest transactions, and the math still checks out billions of years later. Think of it like baking a cosmic cake. If the Big Bang had lasted a fraction longer or burned a degree hotter, that delicate balance of hydrogen and helium would have been thrown off. Too much helium, and stars would have burned through their fuel faster, possibly preventing planets and life from ever forming. Too little, and the first stars might not have ignited at all. The fact that modern observations align so perfectly with those initial 3 minutes of nuclear alchemy is one of the strongest validations of the Big Bang theory. But here's what's even more mind-bending. Almost every helium atom in your party balloons, every hydrogen atom in water molecules, even the lithium powering your phone's battery, they're all relics of this fleeting epoch. While heavier elements like carbon and oxygen were forged later in the hearts of stars, the lightest elements are literally stardust from the first stars, the universe's original factories. So when you take a deep breath or gaze at the sun, you're interacting with matter that's been around since time itself began, unchanged except for its journey through cosmic history. This discovery didn't just confirm the Big Bang, it revealed how finely tuned those initial conditions were. A slight tweak in the strength of gravity or the density of neutrons and the entire periodic table, and perhaps life itself, might never have existed. It's a humbling reminder that we're not just observers of the universe's story, we're made from its very first pages. The universe had a growth spurt, one so violent and sudden it makes the Big Bang look slow motion. In the late 1970s, physicist Alan Guth was wrestling with two cosmic riddles that threatened to unravel the entire Big Bang theory. First, the horizon problem. Why does the cosmic microwave background look almost perfectly uniform in all directions, as if distant regions had somehow coordinated their temperature? Second, the flatness problem. Why is the universe's geometry so precisely balanced between expansion and collapse, like a pencil standing perfectly on its tip? The answers seemed impossible until Guth scribbled a radical idea in his notebook, cosmic inflation. Picture the universe in its first sliver of a second, smaller than a single proton. Then, in less time than it takes light to cross that tiny space, something triggered an exponential expansion, a burst so fierce it stretched the universe by a factor of 100 trillion. That's like blowing up a grape to the size of the observable universe in a fraction of a nanosecond. This wasn't just fast, it was a quantum leap powered by a mysterious field called the inflaton. As space ballooned, it ironed out wrinkles explaining the CMB's smoothness. Regions too distant to ever communicate were once neighbors, stretched apart before they could drift out of sync. Inflation also solved the flatness puzzle. Imagine blowing up a balloon. The larger it gets, the flatter any small patch on its surface appears. Inflation did the same to space-time, stretching any initial curvature until the universe appeared geometrically flat. But Guth's theory didn't just patch holes in the Big Bang. It predicted quantum fluctuations during inflation would leave faint fingerprints in the CMB ripples, later confirmed by satellites like Cosmology and Planck with eerie precision. Yet the wildest implication of inflation, it suggests our universe might be one bubble in an endless cosmic froth, with other bubble universes inflating beyond our observable horizon. Guth's notebook doodles didn't just fix cosmology's cracks, they opened a door to realities beyond our own, where the laws of physics could be radically different. And somewhere in those first frantic moments as spacetime screamed outward, the seeds for galaxies, stars, and us were sown into the fabric of existence itself. At the smallest scales imaginable, far smaller than an atom, smaller than even a proton, the early universe was a frothing sea of quantum chaos. Particles and energy flickered in and out of existence in a dance governed by uncertainty, appearing and vanishing faster than a blink. These fleeting disturbances, known as quantum fluctuations, should have been inconsequential. But in the first sliver of a second after the Big Bang, cosmic inflation took these microscopic ripples and stretched them across the cosmos, forever imprinting them onto the fabric of spacetime. Imagine tossing a handful of pebbles into a still pond. The ripples they create are tiny, barely noticeable. Now picture the pond suddenly expanding to the size of an ocean. Those once small waves would become vast, undulating swells. That's precisely what happened during inflation. Quantum fluctuations, no larger than 1/100th of a billionth of a billionth of a billionth of a centimeter, were magnified to cosmic proportions. These stretched ripples became slight variations in density. Some regions a tiny bit denser, others a fraction emptier, and gravity, always opportunistic, seized onto these differences. Over billions of years, those minute overdensities pulled in more matter, growing like snowballs rolling downhill. The denser areas became the seeds for galaxy clusters, while the emptier regions stretched into the vast cosmic voids we observe today. The fingerprints of these quantum ripples are still visible in the cosmic microwave background, where satellites detect temperature variations of just 1 part in 100,000, the faint echoes of inflation's handiwork. What's truly astonishing is how delicate this process was. If the strength of inflation had been slightly stronger, those quantum ripples would have been stretched too thin, leaving the universe a featureless wasteland without galaxies or stars. Slightly weaker, and gravity would have collapsed those overdensities into black holes rather than galaxy nurseries. Instead, we live in a universe where those quantum whispers were just right, forming a cosmic web intricate enough to birth trillions of galaxies, yet sparse enough to let light travel freely across billions of light years. Even now, every galaxy, every star, every planet including Earth, traces back to those quantum tremors. The very atoms in your body owe their existence to microscopic fluctuations so fleeting they shouldn't have mattered. Yet inflation turned them into the scaffolding of the cosmos, proving that even the tiniest disturbances can shape the grandest structures. It's a humbling thought. The universe didn't just emerge from chaos, it was built by it. In March of 2014, the scientific world erupted with excitement over a discovery that promised to rewrite cosmology. A team using the BICEP 2 telescope at the South Pole announced they detected faint, swirling patterns in the cosmic microwave background patterns that matched predictions for primordial gravitational waves. These weren't just any ripples in space-time, they were echoes from the universe's first trillionth of a trillionth of a trillionth of a second, a potential smoking gun for cosmic inflation. Gravitational waves from this era would be unlike the ones detected by LIGO from colliding black holes. These primordial waves would have been generated by inflation itself, a violent stretching of spacetime so intense it sent tremors rippling through the fabric of reality. Finding them would be like uncovering a fossil from the universe's birth, confirming that inflation wasn't just an elegant theory, but a cataclysmic event that actually happened. The BICEP 2 team's data seemed to show the telltale curl in the CMB's polarization known as B modes, a signature inflation's gravitational waves would leave as they squeezed and stretched photons traveling through the early universe. For a few breathless months, it looked like cosmology had reached a pinnacle. Media outlets declared the discovery of gravitational waves as monumental as the Higgs boson, and physicists cautiously celebrated what might be the first direct evidence of inflation. But cosmic mysteries are rarely so easily solved. When other researchers scrutinized the data, a complication emerged. The signal BICEP 2 detected could have been partially or entirely caused by interstellar dust within our own galaxy, a cosmic mirage obscuring the truth. The Planck satellite, mapping the sky at multiple wavelengths, later confirmed that galactic dust could explain much of the signal. What began as a headline-grabbing revelation became a cautionary tale about the challenges of peering back to the universe's first moments. Yet, even in disappointment, the episode pushed cosmology forward. It sharpened techniques for separating interstellar noise from primordial signals and refined our understanding of what true inflationary B mode should look like. The search for these gravitational waves continues with more sensitive telescopes and better dust mapping methods, because if we ever do capture them, it won't just confirm inflation, it'll give us a time machine to witness the universe's violent infancy, a snapshot of spacetime trembling under forces beyond imagination. Until then, BICEP 2's tantalizing near-miss remains a reminder. The universe's oldest secrets are its most fiercely guarded. While BICEP 2's gravitational wave hunt captivated headlines, another spacecraft was quietly revolutionizing our understanding of the early universe, one pixel at a time. The Planck satellite, launched by the European Space Agency in 2009, wasn't just another telescope. It was a time machine armed with detectors so sensitive they could measure temperature variations in the cosmic microwave background down to a millionth of a degree. For 4.5 years, Planck scanned the entire sky, collecting data so precise it turned the afterglow of the Big Bang into a high-definition cosmic blueprint. What emerged was a portrait of the infant universe with staggering clarity. Planck's maps revealed the CMB's temperature fluctuations, those faint whispers from quantum fluctuations, in exquisite detail, like switching from a blurry black and white photo to a razor-sharp 4K image. But the real magic lay in the numbers. By analyzing these patterns, Planck pinned down the universe's age with unprecedented accuracy, 13.8 billion years, give or take a mere 40 million. That's like measuring the lifespan of a century-old tree to within days. Beyond settling cosmic birthdays, Planck's data became a treasure trove for decoding the universe's ingredients. Ordinary matter, the stuff making up stars, planets, and us, a paltry 5%. Dark matter, that invisible gravitational glue holding galaxies together, 27%. The remaining 68%, dark energy, the mysterious force accelerating cosmic expansion. These numbers weren't just estimates, they were the universe's own recipe, measured with a precision that left physicists in awe. One of Planck's most profound revelations was confirming the universe's near-perfect flatness, a prediction of inflation theory. The satellite's measurements of how CMB light bends around massive galaxy clusters revealed spacetime's geometry on cosmic scales, matching inflation's boldest claims. Yet Planck also threw curveballs. Subtle anomalies in the CMB's large-scale patterns, regions slightly hotter or colder than inflation, predicts hint that our standard model of cosmology might still be missing pieces. Imagine handing a detective a grainy security tape, then upgrading them to crystal-clear footage where every shadow tells a story. That's what Planck did for cosmology. Its legacy isn't just sharper maps or refined numbers, it's the realization that even the universe's faintest whispers, captured with enough precision, can rewrite textbooks. And somewhere in those remaining anomalies, encoded in microwaves older than stars, might lie the next great cosmic revelation. The shape of the universe isn't just a philosophical question, it's written into the very light left over from the Big Bang. For centuries, thinkers wondered whether our cosmos curves like a sphere, bends like a saddle, or lays flat like a sheet of paper. The answer came not from abstract math, but from the cosmic microwave background's subtle patterns, revealing a reality so precisely balanced it defies intuition. The universe is flat. Not just approximately flat, but perfectly flat too, within a razor-thin margin of error. A revelation with staggering implications for how everything began. This flatness isn't about literal two-dimensionality. Instead, it speaks to spacetime's geometry on cosmic scales. In a closed, spherical universe, parallel light beams would eventually converge. In an open, saddle-shaped one, they diverge forever. But in a flat universe, they stay perfectly parallel, with the angles of triangles adding up to exactly 180 degrees, just like the Euclidean geometry we learned in school. The catch: such exact flatness requires an almost impossible fine-tuning of matter and energy densities in the early universe. If the cosmic density had deviated by just one part in 100,000 billion from the critical value needed for flatness, the universe would have either collapsed instantly or ripped apart too fast for galaxies to form. That's where inflation comes in. Like stretching a crumpled sheet of paper until its wrinkles vanish, inflation's exponential expansion flattened spacetime's initial curvature to near perfection. The Planck satellite confirmed this by measuring how CMB light bends, or rather, doesn't bend around massive galaxy clusters. The result, a universe so flat, it's like firing two laser beams side by side across billions of light years and finding they've never deviated by even the width of an atom. Yet this flatness hides a paradox. All the visible matter in the cosmos, every star, planet, and speck of dust, accounts for barely 5% of the density needed to explain this geometry. The rest, a shadowy mix of dark matter and dark energy, whose gravitational effects balance the equation. Flatness isn't just a quirk of geometry. It's a ledger of the universe's hidden ingredients, written in the language of bent light and primordial microwaves. What's truly mind-bending is that this flat geometry isn't static. Dark energy's relentless push is making the universe even flatter over time, stretching space-time so taut that any residual curvature from the Big Bang becomes negligible. Inflation set the stage, but dark energy's encore ensures the cosmos will die not with a bang or a crunch, but with an endless, silent flattening, a slow fade into geometric perfection. So when scientists say the universe is flat, they're not describing a boring, featureless plane. They're pointing to a cosmic tightrope walk, a precision so exact it demands an origin story as violent and transformative as inflation. And somewhere in that razor's edge balance between expansion and density lies the reason galaxies could form, stars could shine, and we could one day look up and decode the universe's shape from the faintest whisper of its birth. In the late 1990s, two teams of astronomers made a discovery so shocking it flipped cosmology on its head. They were studying distant supernovae, exploding stars so uniform in brightness they're called standard candles, to measure how the universe's expansion had changed over billions of years. Everyone expected gravity to be slowing things down, the way a ball tossed upward gradually loses speed to Earth's pull. But the data told a far stranger story. These ancient stellar explosions were fainter than they should have been, meaning they were farther away than anyone predicted. The universe wasn't just expanding, it was accelerating, as if some invisible force was flinging galaxies apart faster and faster. This wasn't just a tweak to the Big Bang model, it was a revelation. Picture a car rolling downhill, only to suddenly hit the gas and speed up instead of braking. That's how baffling cosmic acceleration seemed. The teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees had stumbled upon dark energy, a mysterious repulsive force making up nearly 70% of the universe's content. Einstein had once proposed a similar idea called the cosmological constant, a fudge factor he later called his greatest blunder. Now, it seemed the universe had vindicated him in the most unexpected way. Dark energy's fingerprints are everywhere in the Big Bang's aftermath. The cosmic microwave background shows its subtle tug on spacetime's geometry, while galaxy surveys reveal how it stretched the cosmic web into a sparser, more fractured structure over time. Yet what is it? Theories range from vacuum energy, a property of empty space itself, to dynamic fields that evolve over eons. Some even suggest dark energy could be the echo of inflation, a distant cousin of the force that blew up the universe in its first moments. One thing's certain, without dark energy, the cosmos would look radically different. Its push against gravity delayed the formation of galaxies early on, then ensured they'd never collapse back into a big crunch. Instead, the universe is set on a path toward cold, lonely expansion, where distant galaxies will one day vanish beyond an invisible horizon. And just like the Big Bang's afterglow or the quantum seeds of galaxies, dark energy isn't some abstract curiosity. It's etched into the fate of every atom, every star, and every living thing. A reminder that the universe's first moments didn't just set it in motion, they loaded the dice for everything that followed. The irony, we've only detected dark energy by its shadow, its influence written in the light of dying stars. It's the ultimate cosmic hide-and-seek champion, shaping reality while refusing to show its face. And as telescopes peer deeper into the void, one question lingers. Is dark energy the final twist in the Big Bang story, or just the first clue to something even stranger? The universe's first 3 minutes seem to have everything figured out: hydrogen and helium forged in precise ratios, validating the Big Bang's nuclear alchemy. But lurking in those pristine calculations was a tiny, nagging inconsistency: lithium. According to theory, the scorching conditions of the early cosmos should have produced trace amounts of lithium-7, the lighter isotope of this element, at levels about 3 times higher than what astronomers actually observe in ancient stars. This mismatch, known as the missing lithium problem, has become one of cosmology's most stubborn puzzles, a silent crack in an otherwise flawless edifice. To grasp why this matters, picture baking a cake where every ingredient measures perfectly except one. You double-check your scales, scrutinize the recipe, maybe even question the oven. Cosmologists face a similar dilemma. The equations governing Big Bang nucleosynthesis are exquisitely precise for hydrogen and helium, matching observations to several decimal places. But lithium's shortfall hints at something unexplained, a hidden ingredient, a misapplied law, or perhaps even new physics waiting to be uncovered. The oldest stars in our galaxy act as cosmic time capsules, preserving the chemical makeup of the early universe. When astronomers analyze their light, they find lithium levels hovering around 1/3 of predicted values. At first, scientists thought perhaps these stars had burned off their lithium over billions of years, or that interstellar gas had diluted it. But even the most pristine, unaltered stars, those formed from nearly pure Big Bang material, show the same deficit. The problem only deepens when lab experiments recreate the nuclear reactions of the early universe, confirming the theoretical predictions. If the math is right, where did the lithium go? One tantalizing possibility involves hypothetical particles like actions, dark matter candidates that could have subtly altered nuclear reaction rates in the primordial plasma. Another theory suggests lithium might have been destroyed later by poorly understood processes inside stars, though no known stellar mechanism fits the data neatly. Then there's the radical notion that the universe's expansion rate wasn't perfectly uniform during nucleosynthesis, throwing off lithium production while leaving hydrogen and helium untouched. Perhaps the most intriguing clue comes from lithium-6, lithium's heavier isotope. While lithium-7 is scarce, lithium-6 appears in slightly higher quantities than expected, an imbalance that defies conventional nuclear physics. Some researchers speculate this could point to exotic early universe phenomena, like collisions between cosmic strings or decays of undiscovered particles. For now, the missing lithium remains an open case, a reminder that even our most successful theories have unfinished chapters. Every discrepancy in cosmology is an invitation to look deeper, to question assumptions, and to explore the shadows where current understanding fades. And somewhere in that gap between prediction and observation, between 3-minute-old nuclear ash and 13-billion-year-old starlight, might lie the next revolution in how we see the cosmos. Somewhere in the vast cosmic web, astronomers stumbled upon a pattern so peculiar it made them question whether the universe was playing a trick on them. When scientists mapped the distribution of galaxy clusters and the cosmic microwave background's temperature fluctuations, they expected randomness, a sprawling, chaotic mosaic. Instead, they found hints of eerie alignments, as if some invisible hand had lined up structures across billions of light years. One of the most unsettling is the so-called axis of evil, a mysterious preferential direction in the CMB's fluctuations that seems to defy the cosmological principle, the bedrock idea that the universe should look roughly the same in all directions. This isn't just a minor statistical quirk. The axis of evil refers to temperature patterns in the cosmic microwave background that appear loosely aligned with the plane of our solar system and the orientation of distant quasars, a correlation so improbable it's like rolling a die 100 times and getting the same number every time. If the universe is truly isotropic without preferred directions, such alignments shouldn't exist. Yet multiple studies, including data from the Planck satellite, keep finding these odd large-scale anomalies. Some galaxy clusters even seem to drift along preferred trajectories, like leaves caught in a cosmic river we can't see. What could possibly explain this? One radical theory suggests these alignments might be scars from a pre-Big Bang era, an imprint left by whatever process birthed our universe. If our cosmos emerged from a collision of higher dimensional brains in string theory, or if it's part of a cyclical multiverse, those primordial events could have etched a faint directional bias into spacetime itself. Another idea posits that dark energy or an undiscovered force field might be tugging matter on scales we're only beginning to map. Then there's the unsettling possibility that we're seeing the limits of our own models. The standard cosmological framework assumes uniformity, but what if the universe isn't just a single inflationary bubble? If we're part of a larger anisotropic structure, like a bump on a fractal cosmic coastline, these alignments might be our first glimpse of a reality far stranger than we've imagined. Alternatively, it could all be a grand coincidence, a fluke of statistics that stands out simply because we've looked hard enough. Yet the implications are too profound to ignore. If these large-scale structures truly share a hidden alignment, it wouldn't just tweak our models, it could shatter the foundational assumption that the universe has no center, no preferred direction, no special places. That's why researchers keep probing the data, refining instruments, and hunting for deeper patterns. Because if the axis of evil is real, it's not just an anomaly, it's a cipher left over from the universe's birth, waiting to be decoded. And cracking it might require rewriting the story of everything. The universe is giving us conflicting answers to one of the most fundamental questions in cosmology: how fast it's expanding. This growing crisis, known as the Hubble tension, pits two of science's most reliable methods against each other in a showdown that could rewrite the rules of cosmic evolution. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, which suggests an expansion rate of about 67 kilometers per second per megaparsec. On the other, measurements of nearby supernova and pulsating stars point to a noticeably faster pace, 73. That difference might sound trivial, but after decades of ever-sharpening data, the gap refuses to close. And the implications are staggering. Either we've made colossal observational errors, or the universe is hiding something far stranger than we imagined. To grasp why this divide matters, picture two clocks ticking in perfect sync since the dawn of time. One is set by the primordial microwaves from the universe's infancy, the other by the light of exploding stars in its adolescence. Both should agree on today's time, but they don't. The discrepancy isn't just a rounding error, it's a 5 sigma tension, meaning there's less than a 1 in a million chance it's a fluke. If confirmed, this mismatch suggests that dark energy isn't constant as we've assumed, or that unknown particles flooded the early cosmos, subtly altering its expansion history. Some theorists even speculate about a dark sector of interacting forces that tweaked gravity in ways we haven't accounted for. The plot thickens when you consider how these measurements are made. The CMB method looks backward, extrapolating today's expansion from the universe's baby photos. The supernova approach works forward, using dying stars as cosmic mile markers to gauge how quickly space stretches between them. Both techniques have been refined to astonishing precision, yet they stubbornly refuse to converge. Recent observations of gravitationally lensed quasars and gravitational waves from neutron star collisions have only deepened the mystery, landing squarely in the faster camp. One tantalizing resolution lies in the possibility that our cosmic neighborhood isn't entirely representative, that we inhabit a local underdensity, a bubble of slightly emptier space tugging near by galaxies outward faster than the global average. But even this elegant fix struggles to explain the full magnitude of the tension. Another radical idea, that dark energy evolves over time, growing stronger or weaker in ways our models don't predict. Or perhaps the fabric of spacetime itself has properties we've yet to imagine, an elasticity that changes with scale, like cosmic silly putty stretching differently under varying forces. What makes the Hubble tension so electrifying is that it's not just a problem, it's an opportunity. Every great crisis in cosmology has birthed breakthroughs, from dark energy's discovery to inflation's proposal. Whether this discrepancy reveals new particles, tweaks to relativity, or flaws in our cosmic yardsticks, one thing's certain: the universe is subtly, persistently reminding us that its greatest secrets aren't in the answers we've found, but in the contradictions we can't yet explain. Deep in the constellation Libra, a faint, unassuming point of light holds a secret that has sent cosmologists scrambling to rewrite textbooks. Known as HD 140283, or the Methuselah star, this ancient relic is estimated to be a staggering 14.5 billion years old, older than the universe itself. At least according to initial measurements. That glaring contradiction, a star predating the cosmos that birthed it, has made this aging giant one of the most debated objects in modern astronomy, forcing us to rethink everything we know about the first generation of stars. Discovered over a century ago but only recently studied in depth, the Methuselah star is a cosmic time capsule from an era when the universe was barely a toddler. It belongs to a rare class of stars known as population II stars, metal-poor relics that formed from nearly pristine hydrogen and helium with only trace amounts of heavier elements. Unlike younger stars like our Sun, which are laced with metals forged in earlier stellar explosions, HD 140283's composition suggests it was born from gas that had barely been touched by previous generations of stars. It's like finding a glass of water untouched by human hands, only this water is older than the river it came from. So how could a star possibly be older than the universe? The answer lies in the delicate dance of error bars and cosmic clocks. Astronomers determine the star's age by measuring its brightness, temperature, and composition, then plugging those numbers into models of stellar evolution. Early estimates placed its age at upwards of 16 billion years, a clear impossibility given the universe's 13.8 billion year timeline. Revised calculations, accounting for factors like the star's oxygen content and refined parallax distance measurements, brought that number down, but even the most conservative figures still hover uncomfortably close to the cosmological limit. The Methuselah star isn't just a cosmic oddity, it's a stress test for our understanding of stellar physics and the Big Bang's timeline. Some theorists suggest our measurements might be missing hidden variables like unseen stellar companions or errors in modeling how early stars burn fuel. Others wonder if the universe's age might need subtle tweaking. Perhaps dark energy's influence on cosmic expansion is more complex than we've assumed. Then there's the radical possibility that HD 140283 didn't form in the way we think. Could it be a refugee from a previous cosmic cycle, or the product of exotic physics in the universe's first chaotic moments? What makes this star so invaluable is its rarity. Most population III stars, the hypothetical first generation born from pure Big Bang material, are long gone, burning out in violent supernova that seeded the cosmos with heavier elements. The Methuselah star is one of the few surviving bridges to that primordial era, offering clues about how the first stars ignited in a universe without carbon, oxygen, or iron to cool their birth clouds. Studying it is like interviewing the last living witness to the dawn of time. If only we could decipher its conflicting testimony. For now, the mystery remains unresolved, a tantalizing gap between stellar clocks and cosmic ones. But whether the final answer lies in recalibrated measurements or revolutionary physics, HD 140283 stands as a humbling reminder. Sometimes the universe's oldest objects are the ones with the most to teach us about beginnings. One of the most baffling anomalies in the cosmic microwave background isn't a tiny temperature fluctuation. It's a gaping cold spot spanning nearly 2 billion light-years, lurking in the constellation Eridanus like a cosmic bruise. This frigid region, dubbed the Eridanus supervoid, is so vast and so unexpectedly cold that standard cosmology struggles to explain it. While most CMB variations are mere fractions of a degree, This spot dips a startling 70 microkelvin cooler than its surroundings, as if some immense structure absorbed energy from the primordial light passing through it. At first glance, the simplest explanation seems obvious: a supervoid, an enormous, nearly empty region of space where matter is unusually sparse. As photons traverse such voids, they lose energy climbing out of the gravitational wells created by surrounding denser regions, an effect known as the integrated Sachs-Wolf effect. But there's a problem. The Eridanus cold spot is too big and too cold for even the largest known voids. Simulations suggest a void capable of producing such a temperature drop would need to be unimaginably vast, far larger than any observed structure in the universe. Even then, the odds of such a void aligning perfectly with our line of sight are astronomically slim. This has led to wilder theories. One tantalizing possibility is that the cold spot is a relic of a cosmic defect, a texture left behind by a phase transition in the early universe, akin to cracks forming in ice as it freezes. In the chaotic aftermath of the Big Bang, as fundamental forces split apart, topological defects might have formed in spacetime itself. If one of these defects lingered, it could have subtly altered the CMB's temperature in its vicinity, leaving behind a fingerprint we now observe as the Eridanus cold spot. Then there's the most mind-bending hypothesis of all, that the cold spot marks the collision of our universe with another bubble universe during inflation. According to multiverse theories, our cosmos might be one of countless bubbles in a frothing multiverse. If two bubbles brushed against each other during their explosive expansion, the energy released at their boundary could have imprinted a temperature anomaly on the CMB, a cosmic kiss preserved in microwaves. Observational evidence remains inconclusive. Some galaxy surveys hint at an underdensity in the cold spot's direction, but nothing matching the scale required. Others argue the anomaly might just be a statistical fluke, amplified by our tendency to find patterns in noise. Yet the cold spot refuses to vanish under scrutiny, reappearing in independent analyses of Planck satellite data. Whether it's a void, a defect, or a multiverse scar, the Eridanus supervoid challenges our understanding of cosmic structure. It's a reminder that even our best maps of the universe contain uncharted territories, regions where the rules might bend, or where entirely new physics could be hiding in the cold. The universe was a place of extremes in its infancy, too hot for atoms to form, too chaotic for electrons to settle into orbits. But as the cosmos expanded and cooled, a remarkable transition occurred, the birth of the very first molecules. Among these primordial compounds, one stands out as the pioneer of cosmic chemistry, helium hydride, a fragile union of a helium atom and a proton. For decades, this molecule existed only in theory, a ghostly relic predicted by calculations but never observed in space. Then in 2019, astronomers finally spotted its spectral fingerprint in a distant nebula, solving a cosmic mystery that had lingered since the Big Bang's first breaths. Picture the universe just a few 100,000 years after its birth. The seething plasma of the early cosmos had cooled enough for electrons to latch onto nuclei, forming neutral atoms, mostly hydrogen and helium. But lurking in this newborn atomic soup was an anomaly. Helium, being slightly more chemically inclined than hydrogen, could share its electrons under the right conditions. When a helium atom encountered a hydrogen ion, a bare proton, the two briefly clung together, forming helium hydride. These fleeting molecules were the first chemical handshakes in the universe, the initial step toward the complex molecular tapestry we see today. Theoretical models suggested helium hydride should have been abundant in the early universe, acting as a cosmic stepping stone toward more complex molecules. But as space expanded and temperatures dropped, these delicate bonds were ripped apart by ultraviolet light, leaving no trace in the modern cosmos, or so we thought. Detecting them became a holy grail for astronomers, a way to test our understanding of chemistry's origins. The challenge: helium hydride emits light at a very specific infrared wavelength, one that Earth's atmosphere completely blocks. Enter SOFIA, NASA Airborne Observatory mounted on a modified Boeing 747. Flying above 99% of Earth's water vapor, SOFIA-sensitive instruments peered into NGC 7027, a planetary nebula 3,000 light-years away. Within its swirling gases, heated by a dying star's ultraviolet radiation, the telltale signature of helium hydride shone faintly, a spectral line at 149 micrometers, matching predictions atom for atom. This discovery wasn't just a technical triumph. It confirmed a critical chapter in the universe's chemical evolution, bridging the gap between the simplicity of the Big Bang's aftermath and the molecular complexity that followed. Without helium hydride's brief existence, the first hydrogen molecules might never have formed, stalling the chemistry that later gave rise to water, organic compounds, and eventually the building blocks of life. The irony, the very radiation that destroyed primordial helium hydride in the early universe is what allowed us to detect it in NGC 7027. The dying star's intense UV light recreated conditions similar to the cosmos's infancy, offering us a time machine to witness chemistry's first tentative steps. It's a poetic reminder that the universe's oldest processes are still happening around us, if only we know where to look. Now, with helium hydride's existence confirmed, astronomers have a new tool to probe extreme environments, from the hearts of distant galaxies to the remnants of the first stars. This fragile molecule, once thought lost to time, has become a guidepost to understanding how emptiness transformed into a universe rich with molecules, and ultimately with us. If you've ever misplaced your keys and found them tucked between sofa cushions, you'll appreciate the cosmic scavenger hunt astronomers have been on for decades. Turns out, the universe has been hiding a significant chunk of its ordinary matter, not exotic dark matter, but the stuff that makes up stars, planets, and us. According to Big Bang nucleosynthesis calculations, all the visible matter we observe in galaxies accounts for barely half of what should exist. Like detectives following faint clues, scientists recently traced these missing atoms to the most unexpected place, invisible tendrils of superheated gas stretching between galaxies. These intergalactic filaments form the cosmic web, a sprawling network of gas that connects galaxy clusters like beads on a string. The gas is so diffuse it barely emits any light, yet so hot it reaches temperatures of millions of degrees, making it glow faintly in X-rays. For years, this warm, hot intergalactic medium, or WIM, eluded detection, its presence only hinted at by distortions in the light of distant quasars passing through it. Then, in 2017, researchers used the European Space Agency's XMM Newton telescope to finally catch the WIM ghostly glow. They focused on a pair of colliding galaxy clusters called Able 2794, where gravitational forces had squeezed the gas filaments just enough to make them perceptible in X-rays. Here's why this discovery matters. The Big Bang produced a very specific recipe of hydrogen and helium with trace amounts of heavier elements. By tallying up all the visible matter, stars, gas clouds, planets, we come up short by about 40%. The WIM neatly fills that gap, accounting for nearly all the universe's missing baryonic matter. It's like weighing all the flour you poured into a mixing bowl, then realizing half of it had clung to the sides in a thin, hard-to-see film. Finding these hidden rivers of gas required ingenious detective work. Since the WIM is too faint to observe directly, astronomers looked for telltale absorption lines in quasar light-specific wavelengths where the gas had absorbed photons like a chemical barcode. Others hunted for the Sunyaev-Zeldovich effect, where the gas subtly distorts the cosmic microwave background as it passes through. The breakthrough came when telescopes sensitive to ultraviolet and X-ray emissions spotted oxygen ions, fingerprints of extremely hot gas, lurking in the voids between galaxies. What's truly mind-bending is the scale of this hidden structure. These filaments stretch hundreds of millions of light years, containing more mass than all the stars in the universe combined. They're the scaffolding upon which galaxies grew, seeded by tiny density fluctuations in the primordial universe. Gravity drew matter into these thread-like structures, while dark energy stretched them into a vast diffuse network. Now we're finally mapping this shadowy framework, the backbone of cosmic architecture that's been hiding in plain sight. The implications stretch beyond bookkeeping. This gas isn't just sitting idle, it's constantly cycling into and out of galaxies, fueling star formation and recycling heavy elements forged in supernova. Some of the atoms in your body might have once drifted through these intergalactic currents before being swept up by the Milky Way's gravity. As simulations improve, we're learning how these filaments funnel gas into galaxies like cosmic irrigation channels, sustaining their growth over billions of years. Yet mysteries remain. How exactly does this gas stay so hot? What processes shape its distribution? Future telescopes like Athena and Lynx will probe these questions, hunting for fainter emissions and mapping the web's finer strands. Every new detection peels back another layer of this vast, hidden ecosystem, a reminder that even the ordinary matter in our universe still holds extraordinary secrets. The cosmic hide-and-seek isn't over. We've just found the largest piece of the puzzle. Cosmic inflation couldn't last forever. If it had, the universe would be an empty, featureless void stretched beyond recognition. So how did this runaway expansion slam on the brakes? The answer lies in one of cosmology's most pivotal moments, the end of inflation, a transition so abrupt it left scars we can still see today. Picture a balloon inflating at an impossible speed, then suddenly, its surface crystallizes, locking in every ripple and wrinkle at the instant expansion stops. That's what theorists believe happened when the inflattened field, the mysterious energy driving inflation, stumbled into a lower energy state, releasing its pent-up energy in a firestorm of particle creation. This shift, often called the graceful exit, wasn't gentle. As the inflattened field decayed, its energy flooded the universe with matter and radiation, reheating the cosmos to blistering temperatures and igniting the hot Big Bang we recognize. Think of it like water freezing into ice, a phase transition where the rules of the game suddenly change. Quantum fluctuations frozen into space-time during inflation became the seeds for galaxies, while the universe's geometry snapped into near-perfect flatness. But here's the twist: this transition might not have been perfectly smooth. Some models suggest inflation ended with violent collisions of bubble universes, or even defects in spacetime resembling cosmic cracks. These turbulent moments could have left faint but detectable imprints in the cosmic microwave background. One tantalizing clue: statistically unlikely patterns in the CMB's polarization, known as B modes, which some theories link to gravitational waves generated during inflation's chaotic demise. Others speculate that rare, circular cold spots in the microwave sky, like the Eridanus supervoid, could be bruises from bubble collisions, cosmic fistfights between nascent universes bumping into each other. The details of inflation's end are more than just academic. If we can decode these imprints, we'll know whether inflation was a single, elegant event or a messy clash of competing forces. Was our universe born alone, or are there others out there, their birth pangs forever etched into our sky? The answer might lie in those subtle imperfections, the cosmic equivalent of fingerprints on a windowpane, left by the hand that shaped everything we know. The idea of a multiverse didn't start as science fiction. It emerged from the equations of cosmic inflation like a shadow no one expected. As physicists dug deeper into how inflation might have ended, they stumbled upon a staggering possibility. What if our universe isn't the only one? What if the Big Bang wasn't a solitary event, but just one bubble popping into existence in an endless cosmic foam? This is the wild frontier of eternal inflation, a theory suggesting that once inflation starts, it doesn't stop everywhere at once. Instead, pockets of space stop expanding and become stable universes, like bubbles forming in a boiling pot, while the space between them keeps inflating eternally, birthing new universes without end. Each of these bubble universes could be radically different from our own. When inflation ends in a given region, the local laws of physics crystallize out of the chaos, meaning fundamental constants, the strength of gravity, the mass of electrons, even the number of spatial dimensions might settle into unique configurations. In some bubbles, gravity could be so strong that stars burn out in seconds. In others, atoms might never form, leaving a cold, empty void. Our universe's precise balance of forces, allowing for galaxies, chemistry, and life, could be just one accidental combination in a vast multiversal lottery. The evidence for this mind-bending idea isn't purely speculative. Certain features in the cosmic microwave background, like the infamous cold spot in Eridanus, have sparked debates about whether they're scars from collisions with other bubbles. If two universes brushed against each other during inflation, the energy released at their boundaries might have left a detectable imprint like a cosmic fingerprint smudged onto the sky. Meanwhile, the math behind inflation almost demands some form of multiverse. To halt inflation everywhere simultaneously would require impossibly fine-tuned conditions, like stopping a forest fire with a single drop of water. It's far more likely that inflation continues in some regions while dying out in others, creating a fractal reality where universes sprout endlessly. Critics argue this theory stretches science to its breaking point. If other universes are permanently beyond our observation, can we ever truly test their existence? Yet supporters counter that the multiverse isn't just a fanciful escape. It's a natural prediction of inflation's best supported models. Some even suggest that the elusive theory of everything might not be a single set of equations, but a landscape of possibilities, with each universe exploring a different corner of physical law. Whether the multiverse is real or not, the idea forces us to confront humbling questions. Are the constants of nature truly fundamental or just local bylaws in an infinite cosmic metropolis? If other universes exist, do they harbor life, or are we alone in a sea of sterile bubbles? And if we're one of countless experiments in physics, what does that mean for our place in reality? The multiverse might remain forever untestable, or tomorrow's telescopes might stumble upon its fingerprints. Until then, it stands as cosmology's most daring thought experiment, a reminder that the Big Bang's echoes could be just one voice in a choir we're only beginning to hear. The cosmic microwave background isn't just a snapshot of the early universe, it's a dynamic record of spacetime's earliest struggles with gravity. While its temperature variations tell part of the story, there's another layer hidden in its light. Subtle distortions caused by matter pulling at photons as they traveled for billions of years through an ever-expanding cosmos. This phenomenon, known as the Sachs-Wolf effect, acts like a cosmic echo, revealing how clusters of matter in the infant universe warp the very fabric of reality, leaving faint fingerprints on the CMB we observe today. To understand how this works, picture the CMB as light released when the universe became transparent, a moment often called last scattering. As these ancient photons began their journey, they carried with them a perfect imprint of the universe's temperature at that instant. But their path wasn't unimpeded. When they encountered regions of dense matter, proto-clusters of galaxies waiting to form, gravity's grip altered their energy. Photons climbing out of these deep gravitational wells lost energy, shifting to longer wavelengths and appearing slightly cooler. Conversely, photons falling into underdense regions gained energy, appearing marginally warmer. These shifts, though tiny, collectively painted a map of the universe's matter distribution at just 380,000 years old. What makes the Sachs-Wolf effect so revolutionary is its dual nature. The ordinary Sachs-Wolf effect captures the direct imprint of matter's gravitational pull at the moment of last scattering. But there's a secondary component, the integrated Sachs-Wolf effect, where photons gain or lose energy as they traverse changing gravitational landscapes across cosmic history. Imagine walking uphill as the hill itself is being eroded beneath your feet. The energy you expend depends not just on the hill's initial height, but how it morphs during your climb. Similarly, photons crossing regions where dark energy later stretched spacetime experienced additional energy shifts, encoding the universe's accelerating expansion into the CMB itself. The implications are profound. By studying these distortions, cosmologists can trace how matter clumped together in the universe's first moments, testing predictions of inflation and dark matter models. The Planck satellite's meticulous maps of the CMB's temperature and polarization revealed Sachs-Wolf imprints aligning perfectly with the cosmic web we observe today. Filaments of galaxies tracing back to those primordial density fluctuations. Even more astonishing, the integrated effect offers indirect evidence for dark energy's presence, as its repulsive force alters the gravitational potential of large-scale structures over time. But the Sachs-Wolf effect isn't just a tool for studying the past. It's also a time capsule of cosmic evolution. Some theories suggest anomalies in the CMB's large-scale patterns, like the mysterious cold spot in Eridanus, could be amplified by this effect, hinting at supervoids or exotic physics. Others use it to probe the nature of gravity itself, testing whether Einstein's theory holds across billions of light years. Every photon reaching our telescopes has been on a 14-billion-year odyssey, its energy subtly tweaked by every gravitational hill and valley along the way. In this way, the CMB is more than a static image. It's a living record of spacetime's dance with matter. The Sachs-Wolf effect turns it into a cosmic seismograph, sensitive to tremors in the gravitational fabric of reality. And as we decode these whispers from the dawn of time, we're not just mapping the universe's infancy, we're reading the diary of how it grew up. The universe is supposed to be expanding uniformly, galaxies drifting apart like leaves on a calm river. But in 2008, astrophysicists studying hundreds of galaxy clusters noticed something that sent shockwaves through cosmology. These massive structures weren't just moving with the cosmic flow. They were being pulled en masse toward a single mysterious point beyond the edge of our observable universe. This collective drift, dubbed the dark flow, defies everything we know about cosmic motion, suggesting forces or structures so vast they tug at entire clusters like cosmic marionettes. The evidence comes from the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background caused by hot gas in galaxy clusters. As these clusters move, their motion imprints a faint directional bias on the CMB's photons. When researchers analyzed data from the Wilkinson microwave anisotropy probe and later the Planck satellite, they found clusters streaming at speeds exceeding 600 kilometers per second toward a region in the constellations Centaurus and Hydra. That's not just statistical noise, it's as if someone left the cosmic faucet running and everything's sliding toward the drain. What could possibly exert such a gravitational pull? One spine-tingling possibility is that the dark flow traces its origins to something outside our observable universe, an immense concentration of mass so distant its light hasn't had time to reach us in the cosmos' 13.8 billion-year lifespan. Imagine standing in a vast, foggy field. You can see nearby trees, but beyond a certain point, the fog obscures everything. Now, suppose you notice all the birds are flying in the same direction toward something hidden in the mist. That's the essence of dark flow, an invisible attractor lurking beyond the cosmic horizon. Some theorists speculate this could be a remnant of pre-inflationary physics, a scar from the universe's birth when spacetime was tangled in ways we can't yet model. Others suggest it might hint at a neighboring bubble universe in the multiverse, its gravity leaking into ours. Then there's the unsettling possibility that our universe isn't as isotropic as we thought, that on the largest scales, matter isn't evenly distributed but clumped in ways that defy the cosmological principle. Skeptics argue the dark flow could be an artifact of incomplete data or calibration errors, but follow-up studies, including X-ray observations of hundreds more clusters, have only deepened the mystery. The flow persists, and its scale, stretching billions of light years, makes local explanations flimsy. If this motion is real, it implies structures or forces operating on scales we've never contemplated, where the rules of cosmology might need rewriting. What makes dark flow so electrifying isn't just the anomaly itself, but what it represents: a crack in the door to the unobservable. For all our telescopes and simulations, we may be like flatfish on the ocean floor, sensing tides pulled by a moon we can't see. Whether this flow leads to unknown physics, a multiversal neighbor, or simply a statistical mirage, one thing's certain: the universe still holds moves it hasn't shown us yet. And the greatest show might be playing just beyond the curtain of the observable. Some of the universe's most enigmatic objects might have been born before the first stars even flickered to life. Primordial black holes, hypothetical remnants from the Big Bang's chaotic first moments, could be lurking invisibly throughout the cosmos, hiding in plain sight as dark matter, or even sculpting the earliest galaxies. Unlike the black holes we observe today, forged in the depths of massive stars, these ancient anomalies might have sprung into existence when the universe was less than a second old, born from extreme density fluctuations during cosmic inflation or phase transitions in the searing hot early universe. The idea isn't as far-fetched as it sounds. Picture the infant cosmos as a tempestuous ocean, with quantum fluctuations creating waves so dense they collapsed under their own gravity. Some theories suggest that regions only slightly denser than their surroundings could have pinched off into black holes with masses ranging from a speck of dust to 1,000 suns, or even smaller than an atom. These wouldn't behave like the black holes we know. Microscopic ones might evaporate in a flash of Hawking radiation, while larger ones could persist indefinitely, drifting unseen through galaxies. What makes primordial black holes so compelling is their potential to solve multiple cosmic puzzles at once. If they exist in vast numbers, they could account for the invisible mass we call dark matter. Unlike exotic particles, which experiments have yet to detect, these black holes would be made of ordinary matter, just compressed beyond recognition. Some could have served as seeds for the supermassive black holes now found at galaxy centers, growing voraciously by swallowing gas in the early universe. Others might explain gravitational wave signals that don't quite match predictions from stellar collisions. The hunt for these relics is as creative as their origins. Astronomers have scoured microlensing surveys, watching for the telltale warping of starlight as a dark object passes by. Others study the evaporation of the smallest black holes, searching for gamma-ray bursts that could betray their final moments. Even the subtle heating of ancient gas clouds or distortions in the cosmic microwave background might hold clues, yet the theory isn't without critics. Constraints from gamma-ray observations and stellar dynamics suggest most primordial black holes can't make up all of dark matter, though a hidden population could still be out there. Some models propose they're rare, acting as cosmic oddities rather than dominant players. Others argue they disrupt star clusters or neutron stars in ways we haven't observed. Whether primordial black holes exist or not, their possibility forces us to reconsider the universe's first moments. If confirmed, they'd rewrite the story of dark matter, galaxy formation, and even quantum gravity. And if not, their absence would tighten the limits on how wild the early cosmos truly was. Either way, these phantom remnants remind us that the universe's infancy might have been stranger and more fertile than we ever imagined. The shape of the universe isn't just about flatness or curvature. It's about whether space loops back on itself like a cosmic game of Pac-Man. Imagine walking in a straight line forever only to return where you started, not because you've turned, but because space itself is stitched together in a hidden pattern. This mind-bending possibility, known as the universe's topology, suggests our cosmos might not stretch endlessly, but instead fold into a finite shape, with clues etched into the cosmic microwave background's faintest whispers. Most discussions of cosmic geometry focus on curvature, whether space-time bends like a sphere, saddle, or flat plane. But topology asks a deeper question: even if space is flat, could it have a shape? Picture a sheet of paper, flat, right, now roll it into a cylinder, still geometrically flat, but now with a hidden twist. If you go far enough left, you reappear on the right. Scale that up to 3 dimensions, and you get possibilities like a torus, a donut shape, where space could loop around in multiple directions. If our universe was structured this way, light from the Big Bang might have taken multiple paths to reach us, creating eerie echoes in the CMB identical circles or repeating patterns where the same patch of sky appears mirrored in distant locations. Astronomers have hunted for these cosmic fingerprints for decades. Teams have scanned the CMB for matching circles of temperature fluctuations, statistical twin signatures that would betray a universe folding back on itself. Some studies in the early 2000s even claimed tentative detections of such patterns, though later analyses with higher resolution data from the Planck satellite couldn't confirm them. Yet the search isn't over. If space is finite, its scale might simply be larger than the observable universe, hiding its topology just beyond our horizon. Alternatively, the repeating patterns could be so subtle they're drowned in noise, waiting for next-generation telescopes to tease them out. One tantalizing model suggests the universe could be a dodecahedral space, a 12-sided shape where each face connects to its opposite like a hall of mirrors. Light traveling through such a structure would create kaleidoscopic duplications, making distant galaxies appear in multiple places at once. Another theory proposes a slab topology, where space repeats in just one dimension, like an endless stack of parallel sheets. If true, we might someday spot duplicate galaxy clusters perfectly aligned billions of light-years apart, like cosmic déjà vu. The implications are staggering. A finite universe would mean everything we see, every galaxy, every quasar is just one tile in an infinite cosmic mosaic, repeating endlessly. It would also rewrite our understanding of the Big Bang's aftermath, suggesting inflation didn't just stretch space but wrapped it. And if topology varies across dimensions, say, curled up in some directions but flat in others, it could explain why gravity feels so weak compared to other forces, echoing theories from string theory's hidden dimensions. For now, the universe's topology remains an open question, its answer hidden in the statistical noise of microwaves older than stars. But the hunt itself is a testament to how deeply we've learned to read the cosmos's fine print. Whether space loops, twists, or stretches forever, the very act of asking reshapes our place within it, not just as observers, but as participants in a geometry we're only beginning to trace. While the cosmic microwave background gets all the attention as the universe's oldest light, there's an even more ancient relic hiding in plain sight, one that's been streaming through you this entire video without you noticing. Meet the cosmic neutrino background, a whisper of particles so ghostly they pass through entire planets like they're not even there, born when the universe was barely 1 second old. If the CMB is the afterglow of the cosmos's toddler years, this neutrino sea is a snapshot from its first breath. These neutrinos aren't just ordinary particles, they're survivors from an epoch so extreme, even protons and neutrons hadn't properly formed. Picture the universe right after the Big Bang, a seething soup of energy so dense that light couldn't travel more than a fraction of an inch before colliding with something. In that chaos, neutrinos were among the first particles to break free, slipping effortlessly through the plasma as it cooled. A second later, they decoupled from matter forever, racing outward at nearly the speed of light while carrying secrets about the universe's earliest moments. Detecting them today is like trying to catch smoke with your bare hands. Unlike the CMB's photons, which happily interact with antennas and telescopes, these neutrinos barely acknowledge matter exists. A single neutrino can pass through a light year of lead without a single collision, yet their sheer numbers are staggering. About 300 of them flood every cubic centimeter of space, outnumbering CMB photons by 1,000,000,000 to 1. If you hold out your hand, trillions of these cosmic ghosts slice through it every second, remnants of a time when the entire universe was hotter than the core of a supernova. The hunt to capture these elusive particles is pushing physics to its limits. Projects like the Princeton Tritium Observatory for Light, Early Universe Massive Neutrino Yield, or TOLME, aim to trap relic neutrinos using ultra-cold detectors lined with radioactive tritium. The idea, when a relic neutrino interacts with tritium, an event rarer than winning the lottery while being struck by lightning, it could produce a faint signal, a tiny bump in energy that betrays the neutrino's presence. Other proposals involve observing how these ancient neutrinos subtly slow the spins of rotating molecules, or even exploiting quantum tricks to amplify their vanishingly weak interactions. Why go to such extremes? Because this background is a time capsule from an era no telescope can peer into. The patterns etched into these neutrinos could reveal whether inflation truly happened or if exotic particles once roamed the primordial plasma. Their energies might even hint at dimensions beyond the three we know, and if we ever detect them, it would be like finding a fossilized whisper from the moment time itself began ticking, a direct line to the universe's very first second. Until then, these ghostly particles remain both everywhere and nowhere, a cosmic sleight of hand reminding us that the past isn't dead, it's flowing through us unseen and untouchable, waiting for the day we learn its language. The cosmic microwave background isn't just a snapshot of the early universe's temperature, it's also a Polaroid, capturing the direction in which its ancient light vibrated. Hidden within these faint polarization patterns lies what could be the ultimate smoking gun for cosmic inflation, a specific swirl known as B-mode polarization. Unlike the simpler E-modes, which arise from density fluctuations in the primordial plasma, B-modes carry the signature of something far more exotic: gravitational waves from the universe's first trillionth of a second, when inflation stretched spacetime itself to unimaginable scales. Picture the early cosmos as a stormy ocean. Inflation's violent expansion would have sent shockwaves rippling through spacetime, gravitational waves so powerful they could twist the polarization of photons as they traveled. These twists imprint a distinctive curl on the CMB's polarized light, like fingerprints left on a foggy mirror. Spotting this pattern would be like finding the fossilized ripples of the Big Bang's birth pangs, direct evidence that inflation wasn't just a clever theory but a cataclysmic reality. The hunt for B-modes has been one of cosmology's most high-stakes detective stories. In 2014, the BICEP 2 team at the South Pole thought they'd cracked the case, announcing a detection of these elusive swirls. For a moment, it seemed we'd glimpsed inflation's gravitational waves, but the celebration was premature. Further analysis revealed that interstellar dust in our own galaxy could mimic the signal, a cosmic red herring. The Planck satellite later confirmed that much of the observed pattern was indeed dust, leaving the inflationary B-mode signal still at large. Yet the search hasn't ended, it's evolved. New generations of telescopes, like the Simons Observatory and the upcoming Light-Bird satellite, are deploying with unprecedented sensitivity, scanning the sky at frequencies designed to separate galactic dust from true primordial signals. These instruments aren't just looking for a needle in a haystack, they're trying to spot a specific kind of needle while filtering out an avalanche of glitter. What makes B-modes so revolutionary isn't just their connection to inflation. If detected, their strength could reveal the energy scale at which inflation occurred, effectively telling us how powerful the universe's first engine truly was. A strong signal would point to inflation driven by ultra-high-energy physics, perhaps even linking to grand unified theories or quantum gravity. a weaker signal or none at all, might force us to reconsider inflation altogether, sending theorists back to the drawing board. But there's a twist. Even if we never find inflationary B-modes, their absence would speak volumes. It might hint that inflation happened at lower energies than we thought, or that the process was far subtler, leaving no gravitational wave fingerprints. Alternatively, it could mean we're missing something fundamental about how polarization works in the early universe. The stakes are so high because this isn't just about confirming a theory. It's about peering into a regime where the laws of quantum mechanics and gravity collide, a domain no lab on Earth can recreate. The irony is exquisite. To understand the universe's largest scale structure, we're studying the faintest possible imprints on its oldest light. And somewhere in those delicate curls of polarized microwaves, or their stubborn absence, might lie the answer to how everything began. Whether B-modes confirm inflation, challenge it, or remain just out of reach, they're a testament to how far we've come in reading the universe's deepest diary, one whispered entry at a time. For decades, the Big Bang wasn't the only game in town when it came to explaining the universe. Competing theories like the steady-state model argued passionately that the cosmos had no beginning, that it simply was, eternal and unchanging, with new matter continuously popping into existence to fill the gaps as galaxies drifted apart. It was an elegant idea, offering a universe without creation or destruction, where the overall view stayed the same no matter when or where you looked. But in the end, it wasn't elegance that decided the winner. It was evidence, and the discovery of the cosmic microwave background didn't just challenge alternative theories, it dismantled them. The steady-state theory's fatal flaw was its prediction of a universe without a definitive starting point. If galaxies were forever drifting apart while new matter filled the void, there should be no relic radiation bathing the cosmos, no afterglow from a hotter, denser past. But Pensier's and Wilson's hissing antenna changed everything. The CMB wasn't just background noise, it was the unmistakable signature of a universe that had once been scorching hot and was now cooling as it expanded. This wasn't a minor inconsistency, it was a direct contradiction. The steady-state universe had no mechanism to produce such a uniform, all-pervading glow, let alone one with the precise spectrum of blackbody radiation matching a cooling fireball. Then came the knockout punch, the CMB's temperature fluctuations. In a steady-state cosmos, matter was assumed to form continuously, but there was no natural explanation for why the universe's oldest light would carry the faint imprints of density variations, those quantum ripples stretched by cosmic inflation. These fluctuations required a dynamic origin, a moment when the universe transitioned from a hot, dense state to the cooler, structured cosmos we see today. Without a Big Bang, there was no way to explain why galaxy clusters trace back to those subtle wrinkles in spacetime, or why the ratio of hydrogen to helium matches calculations of nuclear fusion in the universe's first minutes. Other challenges fell just as hard. The tired light hypothesis, which tried to explain redshift without expansion by suggesting photons lost energy over vast distances, couldn't account for the CMB's specific temperature or its uniformity. Eternal inflation models, while sharing some similarities with the Big Bang, still relied on a version of cosmic birth that left distinct imprints, ones we now see confirmed in the CMB's polarization patterns. Even more exotic ideas, like cyclical universes or plasma cosmology, struggled to explain why the cosmos looks precisely as it should if it erupted from a singular, explosive beginning. Yet the triumph of the Big Bang wasn't just about disproving rivals, it was about predictive power. The steady-state theory reacted to observations, the Big Bang anticipated them. It foresaw the CMB's existence before Pensier's and Wilson stumbled upon it. It correctly calculated the abundances of light elements before telescopes could measure them. And when satellites like COBE and Planck mapped the CMB's minute fluctuations, they matched inflationary models with breathtaking accuracy. Competing theories weren't just wrong, they were unnecessary, like trying to explain sunrise with mirrors and lanterns when Copernicus had already traced Earth's orbit around the Sun. That's not to say the Big Bang is complete. Dark energy, quantum gravity, and the nature of inflation remain open questions. But what makes it science's leading origin story isn't dogma, it's the mountain of evidence supporting it. The CMB didn't just silence rival theories, it turned cosmology into a precision tool, capable of measuring the universe's age to within a sliver of its actual lifespan. And as long as new discoveries keep aligning with its predictions, from the distribution of galaxies to the whispers of gravitational waves, the Big Bang's dominance isn't just unshaken. It's the foundation on which we're still building our understanding of everything. From the cosmic microwave background's whisper to the enigmatic dark flow pulling galaxies toward the unknown, these 25 discoveries have rewritten the story of our universe. Each revelation peels back another layer of cosmic mystery, reshaping not just how we see the stars, but how we understand reality itself. The Big Bang was once a speculative idea. Now, it's a detailed chronicle written in ancient light, quantum ripples, and phantom forces like dark energy. We've traced helium in party balloons back to the universe's first 3 minutes, found galaxies racing away from us faster than light should allow, and glimpsed hints of bubble universes beyond our cosmic horizon. Consider how inflation stretched quantum fluctuations into galaxy clusters, or how primordial black holes might lurk unseen as dark matter. Think about the cosmic neutrino background streaming through you right now, untouched since the universe's first second. Ponder the Hubble tension, where the cosmos gives two different answers for its own expansion. Rate a paradox that could unravel our understanding of dark energy. These aren't just trivia, they're the pillars of modern cosmology, each one a thread in the tapestry of existence. But here's the thrilling part, we're nowhere near the end. The Eridanus cold spot, the missing lithium problem, the phantom pull of dark flow. These anomalies are clues that the universe still holds cards close to its chest. Future telescopes could detect inflationary gravitational waves, proving multiverse theories. Lab experiments might trap relic neutrinos, offering a snapshot of the Big Bang's first heartbeat. Or perhaps the next breakthrough will come from somewhere entirely unexpected, flipping the script once again. So as we look up at the night sky, let's not just see points of light, let's see the unanswered questions. What's beyond the observable universe? Are we alone in a sea of bubble realities? How did something emerge from nothing? Drop your favorite cosmic mystery in the comments and keep wondering. Because the greatest discovery might not be in a textbook yet. It could be hiding in the next beam of starlight, waiting for someone bold enough to ask the right question. The universe's story is still being written, and you're here to witness it unfold.